Somewhere in the outer dark, a storm has been turning. Not for a decade, not for a century, for 400 years, longer than any human institution that still stands. When this storm began, Galileo was still alive. Shakespeare had just died. The telescope itself had barely been invented, and on a planet no human eye had ever seen, a vortex the size of Earth was tightening its coils. That planet is Neptune, and the storm is still there. Now, for the first time, the James Webb Space Telescope has looked inside it. What it found was not just surprising, it was, in a quiet and unsettling way, profound. This video is about that discovery, but it's also about something larger. What it means to be a conscious creature in a universe that has been running its own experiments in the dark long before any mind existed to watch. Let's start at the beginning. Not Neptune's beginning, ours. Most of us learned the planets in order. Mercury, Venus, Earth, Mars, the rocky ones, then the gas giants, and then, at the very edge of the schoolroom solar system, Neptune. Neptune was always the afterthought. Too far to see, too cold to matter. A blue dot at the edge of a diagram. That framing, it turns out, is almost completely wrong. Neptune is not a gas giant. It belongs to a different category entirely, what planetary scientists call an ice giant. And that distinction is not cosmetic. It changes everything about how the planet behaves. Think of Jupiter as a mostly hydrogen world, an enormous sphere of gas that, if you fell into it, would compress and heat you, but never offer a solid floor. Neptune is different. Its bulk is not gas. It is water, ammonia, and methane, but under pressures so extreme that those familiar molecules are crushed into forms we barely recognize. Not ice in the sense of your freezer. Hot, dense, electrically conductive, a state of matter sometimes called a superionic fluid. The word ice here is a classification, not a temperature. At Neptune's core, the pressure may be millions of times that of Earth's atmosphere. And water, under those conditions, does something extraordinary. It rains diamonds. Carbon atoms, stripped from methane by the pressure, crystallize and fall as solid diamond precipitation toward the core. Not metaphorically, literally. Neptune may have a diamond ocean at its center. We are already inside a world that defies ordinary intuition, and we haven't even reached the storm yet. Neptune sits 4.5 billion kilometers from the Sun. Light takes 4 hours to make that journey. When you look at Neptune, you are not seeing it as it is. You are seeing it as it was. There is a delay baked into every observation we make of distant things. All astronomy is, in a sense, archaeology. Neptune receives about 900 times less sunlight than Earth, and yet, somehow, it has the fastest winds in the solar system, 2,000 kilometers per hour. Supersonic. On Earth, a Category 5 hurricane tops out around 300 kilometers per hour. Neptune's winds are nearly 7 times faster, and they are constant, planetary, global. How does a planet that barely receives any solar energy generate winds like that? That question has haunted atmospheric physicists for decades. The leading answer involves internal heat. Neptune radiates more than twice as much energy as it receives from the Sun, meaning it has its own heat engine buried inside it, a remnant of its formation that has never cooled. Think of it like a pot of water that has been simmering since the solar system formed. 4.5 billion years of slow internal release, driving convection, driving circulation, driving storms. And the most dramatic expression of that circulation, the thing we have come to call the Great Dark Spot. We first saw it clearly in 1989. Voyager 2, the only spacecraft ever to visit Neptune, swept past at about 5,000 kilometers above the cloud tops. The encounter lasted hours, a single pass, one flyby, and then Voyager continued outward into interstellar space, never to return. But in those few hours, the cameras caught something that stopped scientists cold, a dark oval vortex in Neptune's southern hemisphere, rotating counterclockwise, stable, ancient-looking, roughly the width of the entire Earth. They called it the Great Dark Spot, an obvious echo of Jupiter's Great Red Spot. 2 superstorms on 2 planets, the solar system repeating a pattern, but the comparison revealed something strange almost immediately. Jupiter's Great Red Spot has been observed since the 1600s and is remarkably stable. Shrinking, yes, but persistent. Neptune's did something different. By 1994, when the Hubble Space Telescope turned toward Neptune, the original Great Dark Spot was gone, vanished, as if it had never existed. But then, in a different latitude, a new dark spot had appeared. Neptune's storms don't simply persist, they die and are reborn. They cycle. They are, in some sense, planetary breathing, a rhythm we had never seen before. Which brings us back to the question, if a storm was already raging when Galileo died and continued through the Enlightenment, through the Industrial Revolution, through both world wars, what exactly are we looking at? The current Great Dark Spot, a new one first confirmed in 2018, is in Neptune's northern hemisphere, and it has proven remarkably stubborn. For years, it held its shape. Then it seemed to drift toward the equator, which, in Neptune's atmosphere, is a known death sentence for dark spots. Scientists began to predict its dissolution. Then, it did something that no model had predicted. It reversed direction, moved back toward the pole, stabilized, and spawned a smaller companion vortex, a secondary storm orbiting the main one like a moon around a planet. That companion vortex, nicknamed the dark spot's shadow, is one of the most unexpected atmospheric features ever detected on an outer planet. It tells us the storm is not a passive structure, it is a dynamic system, interacting with the atmosphere around it, shedding energy, pulling smaller structures into its influence. That word, influence, hold on to it, because what James Webb revealed about this storm is precisely a story about influence, about how the vortex reaches upward through Neptune's atmosphere and reshapes the layers above it. The James Webb Space Telescope launched in December 2021. It is the largest, most powerful space telescope ever built. Its primary mirror is 6.5 meters across, about the height of a two-story building. But Webb's real power is not size, it is wavelength. Webb sees in the infrared, heat rather than visible light. That matters enormously for Neptune because the planet's atmosphere is largely opaque in visible wavelengths. Visible light bounces off cloud tops, infrared penetrates deeper. With Webb, we could finally see not just the storm's face, but its structure, layers below layers, a depth of atmosphere that Voyager and Hubble could only hint at. When Webb's first Neptune images were released in 2022, the scientific community and the public both stopped to stare. Not because of the storm, but because of the rings. Neptune has rings. We knew that, but we had never seen them like this. Bright, detailed, structured, almost Saturn-like in their clarity. Webb showed us those rings in a way that decades of prior observation had failed to deliver. It was the first hint of how radically this telescope would change what we knew about the outer solar system. But the rings were the prologue. The storm was the chapter we had been waiting for. When Webb's instruments were pointed at the Great Dark Spot region, the data came back layered, literally. What they found was a multi-tiered structure, different altitudes of the storm showing completely different behaviors. At the top, in the stratosphere, high above where clouds form, Webb detected something unexpected, a brightening, a warm cap sitting directly above the storm's eye. This is a phenomenon called a stratospheric hot cap. We see analogues of it above Earth's polar vortex. But in Neptune's case, this heat signature sits over an active storm, implying the storm is pushing energy upward. Think of it like pressing your thumb into a waterbed. The pressure you apply does not stay where your thumb is. It propagates outward and upward through the medium. The storm is doing this to Neptune's entire upper atmosphere. It is not just a weather event in one layer. It is a vertical engine, reaching from deep in the troposphere all the way up into the stratosphere. That changes the model. Before Webb, we thought of Neptune's dark spots as surface phenomena, relatively shallow disturbances in the top cloud deck. Webb tells us they are not shallow, they are deep. They root somewhere far below what we can see, and they reach above it too. The storm is, in effect, an atmospheric column, a churning pillar of gas and chemistry that spans a vertical distance we are only beginning to measure. Now let's talk about the chemistry, because what is inside this column is, in its own way, as astonishing as its scale. Neptune's atmosphere is primarily hydrogen and helium, about 80% hydrogen, so far unremarkable. But the remaining fraction contains methane. Methane is why Neptune is blue. It absorbs red wavelengths of sunlight and reflects blue. The blue of Neptune is, quite literally, the fingerprint of a molecule. But in the storm, methane behaves differently. Webb's spectroscopic instruments detected anomalous concentrations of methane ice clouds directly above the Great Dark Spot region. This is significant. Methane ice clouds are typically found at specific pressure altitudes. Their appearance above the storm suggests that the vortex is driving upwelling, physically pumping material from deeper, warmer layers up toward the cold, high atmosphere. You've seen this on Earth. When a thunderstorm is extreme enough, it punches through the tropopause, the boundary layer between the troposphere and stratosphere, and injects moisture into regions that are normally bone dry. Neptune's Great Dark Spot does something analogous, but with methane at planetary scale continuously for what may be centuries. Webb also detected something in the companion dark spot, the smaller vortex that shadows the main one. The companion appears to lack this methane upwelling signature entirely. Same planet, same storm system, two vortices and completely different internal chemistry. This tells us the storms are not identical copies. They are individuals. Each storm on Neptune is a unique atmospheric event, shaped by the local conditions at the moment of its formation, retaining that character even as it evolves. There is something philosophically disorienting about that. We tend to think of weather as interchangeable. A storm is a storm. Neptune suggests otherwise. A storm may have a signature, an identity. Now, let's talk about longevity, because this is where the numbers become genuinely difficult to hold in the mind. Earth's most persistent storms, the ones we consider long-lived, might last a few weeks, a few months for an unusually stable system. Then they dissipate. The Great Red Spot on Jupiter has persisted for at least 350 years. That is already nearly incomprehensible. Neptune's current storm system, accounting for the cycling behavior, the appearance and disappearance and reappearance of dark spots in a pattern consistent with a single underlying atmospheric dynamic, may represent a process that has been running continuously for 4 centuries. 400 years. No continent, no ocean, no biosphere. Just rotating gas over and over and over on a world no living thing has ever touched. The question this provokes is one that science often brushes aside as unscientific, but I want to sit with it for a moment. Does an event that occurs without any witness, without any consciousness present to register it, exist in any meaningful sense? I am not asking this in the philosophical hair-splitting sense. I am asking it as a practical challenge. The storm on Neptune has been happening. That is an objective fact. It does not need us. And yet, the moment we observe it, the moment James Webb translates its infrared signature into data that a human mind can read, something changes. Not the storm, the relationship. Observation is not passive. In physics, we know this formally from quantum mechanics, but it is also true in a larger cultural sense. When we look, we become responsible for what we see. James Webb's images of Neptune do not just advance planetary science. They quietly demand that we reckon with the scale of what exists beyond the reach of human experience. Let's return to the data now, because Webb's observations of the storm also produced a result that has specific implications for how storms form on ice giants. The prevailing model before Webb suggested that dark spots form when the lower atmosphere, the deep troposphere, generates instabilities that then rise and manifest at visible cloud levels. Webb's data suggests something more interesting, that the storms may be maintained from below by continuous convective forcing, constant upwelling of material from very deep layers. Not a one-time event, but a sustained process. This would explain longevity. A storm that is continuously fed from below does not simply run out of energy the way a terrestrial hurricane does when it crosses land. On Earth, hurricanes are heat engines. They feed on warm ocean surface water. Take that away and they die. Neptune's dark spots may feed on internal planetary heat that will not be taken away for billions of years. They are not borrowing energy from the sun. They are drawing on the planet's own ancient reservoir. the leftover warmth of formation still slowly leaking outward after 4.5 billion years. It also raises a question about the cycling behavior, why storms appear, disappear, and reappear. Webb's data suggests the deep convective engine never fully turns off. What we see at cloud level may be more like a visible symptom than the disease itself. The dark spots may be like sunspots, surface expressions of a deep magnetic or convective cycle. When the conditions align, the vortex breaks through. When they don't, it recedes. But the underlying engine persists. If that model is correct, then the storm that has been raging on Neptune for 400 years is not 400 years old. It is 4.5 billion years old. We are watching the oldest weather in the solar system. Let that settle for a moment. Now let's talk about what this means for the search for other worlds. Because Neptune-like planets, ice giants, are, it turns out, extremely common in the galaxy. The Kepler Space Telescope and its successor, TESS, have identified thousands of exoplanet candidates. A significant fraction of them, perhaps the majority, appear to be what astronomers call sub-Neptunes, or super-Earths, worlds in the size range between Earth and Neptune. This makes Neptune not an afterthought, but a template. Our ice giant is, in galactic terms, one of the most common types of planet, which means the processes Webb is revealing on Neptune, the storm dynamics, the deep convection, the atmospheric chemistry, are likely replicated across millions of worlds. On how many of those worlds are storms churning right now? Ancient, relentless, witnessed by nothing. On how many is there something, nor someone, looking back? The Webb telescope will continue observing Neptune over the coming years. Each new data release adds another layer of understanding, but it also adds another layer of weight. One of the most intriguing follow-up questions currently being investigated: does the storm produce aurora-like phenomena? Neptune has a magnetic field, tilted at 47 degrees from its rotation axis, which is bizarre. Earth's magnetic field is tilted about 11 degrees. Neptune's is tilted nearly 5 times more, and it doesn't even originate from the geometric center of the planet. It's offset. This creates a magnetic environment unlike anything we experience on Earth, one that interacts with the solar wind in chaotic, complex ways. And a vortex in the upper atmosphere might interact with that field in ways Webb is only beginning to probe. There is also the question of what is physically below the storm. The dark spots we see are in the troposphere, but Neptune's troposphere transitions into a region called the, and this is the official term, slushy ice layer. A zone of compressed water and ammonia behaving like neither liquid nor solid. The storm's roots may extend down into that region, into a material state we cannot replicate on Earth, into chemistry that exists nowhere else in the known universe except in the interiors of ice giants. This is the boundary of our knowledge, not a soft boundary, a hard one. We cannot drill into Neptune. We cannot send a probe through its atmosphere the way Galileo did with Jupiter. Not yet. There have been proposals, serious, funded to concept proposals, for a dedicated Neptune orbiter and probe mission. It is called, at various stages, the Neptune Odyssey concept. It would take 12 to 16 years to reach Neptune. We would launch it and then wait, a generation of scientists handing the mission from one cohort to the next. There is something moving about that. The people who would design this mission would not live to see all of its results. Science on this scale is an act of faith in the future. In the meantime, Webb is what we have. And Webb, operating from a gravitational parking spot 1.5 million kilometers from Earth, has already rewritten the Neptune chapter of planetary science. The data it has returned about the storm is being incorporated into new atmospheric models. Those models are being applied not just to Neptune, but to the ice giant exoplanets that Webb itself is beginning to characterize. One discovery feeding directly into the next. That is how science actually advances, not in isolated revelations, but in cascades. Let me close with the frame I opened with. A storm, 400 years old, no witness. Human civilization has a deep assumption woven into its languages and its religions and its philosophies, that events have meaning only in relation to minds that can register them. The universe, politely but insistently, disagrees. It has been running its processes, stars forming, black holes consuming, ice giant storms circling, regardless of whether any mind was available to give them meaning. And yet, here we are, a species that evolved on a small, warm, wet rock, pointing a gold-plated mirror at a storm we will never touch, on a planet we have visited exactly once, and reading the chemistry of its clouds. That is not a small thing. That is, arguably, the most extraordinary thing that has ever happened in this solar system. The moment when matter became organized enough to look at itself and ask, what is happening out there? The storm will keep turning. It will still be there tomorrow, next year, long after every person alive today is gone. But now, for the first time, it has been seen. And that changes the storm not at all, and changes us completely. If this video gave you something to think about, subscribe. We go this deep every week. And leave a comment. What does it mean to you that something this vast exists and we almost never look?